This video is going to be another follow along type of video. I'm going to be doing a few extra problems on infinite sequences and series. These are from a test prep book that I found online. Okay, so I would recommend you pause the video after you see the problem, try the problem first on your own, and then unpause it to see how I think through it, if it helps you in any way. And then, of course, you can check your solution with my solution as well. Okay, number one, does this series converge or diverge? So go ahead and try this first on your own. Okay, this one's pretty simple. If you realize that we can just use the test for divergence. As a rule of thumb, you should probably always try the test for divergence first for any infinite series. Okay, so if we take the limit as n goes to infinity of this sequence, what's the limit? It's 1 over e. Realize that 1 plus 1 over n to the n power, and if we take the limit as n goes to infinity of that, it's e. So if it's to a negative n power, it's just e to the negative 1, or 1 over e. Okay? Since this limit is not 0 by the test for divergence, the series diverges. Okay? So this is probably the easiest way to determine the convergence or divergence of this guy. Test for divergence. Number two, find the interval of convergence of this power series. So go ahead and try this first on your own. So how did I approach this? Well, I thought to write this guy in summation notation first. Then it becomes familiar territory, at least for me. So this is convenient that they wrote it like this because we can easily find the pattern. The x to some power is x to 0, x to the first, x to the second, x to the third. So it looks like it's sequentially increasing. It's alternating sign, we realize. So it's plus, minus, so on and so forth. What about the bottom? Well, there's a 3 here, there's a 9 here, there's a 27 here. So it looks like it's 3 to the 0, 3 to the first power, 3 squared, 3 cubed, so on and so forth. Now, what's this 2 and this 6? Well, it looks like it's 2 factorial over here and 3 factorial over here. So probably a 1 factorial over here, which is just 1, and 0 factorial over here, which is just 0. Okay, so we put all these pieces together, and this is the summation notation. Now that we have this form, we can use the ratio test to get our radius of convergence, and that gets us on the path to getting the interval convergence, okay? So we go through the motions of the ratio test. You can definitely pause the video. I'm not going to explain every single step here. We do the ratio test, we get 0 as the result. So what does that mean? Since the limit does not depend on x, and it's always less than 1, remember what the ratio test says? The ratio test says the series is convergent if it's less than 1. Since this is always less than 1, that means the interval of convergence is negative infinity to infinity. We went over this in the radius and interval convergence practice problem set. So I would recommend you look over that as I explained it a little more in detail over there, if you still need an explanation. Okay, number 3. If P of x is this guy, is a Taylor polynomial for f of x, write a third degree Taylor polynomial for m of x equals integral from negative 1 to x p of t dt. So go ahead and try this one. So the key here is to remember we can integrate and differentiate power series. So we can find m of x by integrating this guy over here. Okay? If we do that, we know how to integrate this. It's just power rule. It becomes 2t plus 3t plus 1 squared over 2 minus 6t plus 1 cubed over 3. Evaluate from negative 1 to x. We found the antiderivative, and we're going to use fundamental theorem calculus up here. Okay, plug in the upper bound minus plug in the lower bound. That's what happened here. And if we simplify, this is our answer. This is our m of x. And it's coincidentally, or maybe it was intended, it's already a third degree polynomial. So that's our answer. Now, a better answer is to make the first degree term in the form this guy. So we can factor out a 2 from these first two terms. So it becomes 2 times x plus 1, so that it matches more the power series form, because we should write this guy as x plus 1 to the first power to match the power series representation. So one way to do it is just factor out the 2 from these two terms. And that does it. Okay. So if this were the AP exam FRQ, I don't know if they would mark you off if you wrote it like this as your final answer. So you should know how to do this to be safe. And you should understand why, as I just explained, why we should write it like this. Okay. Number 4, does this series converge absolutely, converge conditionally, or does it diverge? All right. We probably want to use the ratio test because if the ratio test, the result of the ratio test is less than 1, the ratio test says that the series is absolutely convergent. So maybe let's directly try to use the ratio test right from the beginning. And it's probably a good idea to use that because there's a factorial in this series. Remember, the ratio test gets rid of factorials nicely. Okay, so we go through the motions of the ratio test. Again, I'm not going to explain every single step. You can check it out by pausing the video. The limit is 0, which is less than 1. So this series is absolutely convergent. It converges absolutely. So we directly just use the ratio test to determine absolute convergence. Okay, number 5, find the value of A so that the radius of convergence for the series is 1/4 and A is greater than 0. So go ahead and try this one. This one's a little different than problems you've probably seen before. Okay, so it's asking about radius of convergence. So we probably want to use the ratio test if we're just totally lost. If this was an AP free response question and you're totally lost, you probably want to do at least something to possibly get some credit, partial credit. So radius of convergence, probably let's do the ratio test. Okay, we go through the motions. Again, I'm not going to go through all the algebra. You can check it out on your own. Okay, the ratio test gives us a squared times absolute value of x minus 1. Okay, so the ratio test says this guy would converge if this guy, a squared times absolute value of x minus 1 is less than 1. Or we can move this a squared to the other side. So this looks more familiar, right? Absolute value of x minus 1 is less than 1 over a squared. So this is our radius of convergence, 1 over a squared. And the problem tells us that our radius of convergence needs to be 1/4. So 1 over a squared equals 1 over 4. What does that mean? A has to be? A is plus or minus 2. But since they tell us that a is bigger than 0, a is positive, we only keep a equals 2, and that's our answer. Okay, so once again, if you were totally lost as to what to do, the key word was radius of convergence. So maybe just try the ratio test and you might have gotten an idea after you got this what to do. Okay. Number 6 is g of x is e to the sine x. Use the 4th degree Maclaurin polynomial to approximate g prime of 0.3. So go ahead and try this one. So let's get the 4th degree Taylor polynomial, Maclaurin. I'm just going to say Taylor polynomial. That's what most people say. So we're going to start with the Maclaurin series of e to the x. We know what that is. Hopefully you memorized it, actually. It's this guy in an expanded form. Okay. So we can find the Maclaurin series for e to the sine x. Wherever there's x, replace it with sine x. That's what I did over here. So we can find g prime by differentiating right here. Okay. And the Taylor polynomial, Maclaurin polynomial, would be going up to only the 4th degree term. That's what I meant to say over here. The g prime is approximately equal to derivative of 1, 0. Derivative of sine is just cosine. We need the power of 1 chain rule here, and the power of 1 chain rule here, power of 1 chain rule here, so on and so forth. Okay? And there'll be more terms, but as I said, we only want the 4th degree Maclaurin polynomial, Taylor polynomial. I'm saying both still. So we cut off everything that is higher degree. Okay. So now we just use this guy to approximate g prime of 0.3. We need a calculator. Clearly, you should get something like this afterward. Okay. Number 7, part A. Find the sum of the series. If the exact sum is not possible to find it accurate to 4 decimal places. So this is our series. So can you find the sum? We realize that this is a geometric series with r equals -half. Okay? And we know very well how to find the sum of an infinite geometric series. It's the first term over 1 minus common ratio. The first term is 3. Common ratio is negative half. So it's 3 over 3 halves, which is 2. That's our answer. Okay, now how about for this series? Summation as n goes from 1 to infinity, negative 1 to n, e to the negative n cubed. Can we find the sum of this one, or should we approximate it? Okay, so if we're able to find the sum of it, it's probably going to be one of the series that you studied quite in depth. For example, geometric series. One of the Taylor series, like e to the x, sine x, cosine x. The other possible case is a telescoping sum. This is not a telescoping sum because it should look like a partial fraction decomposition if you remember. Okay, this is not a geometric series, clearly. And this doesn't really look like any of those 3 Taylor series that you remember, e to x, sine x, cosine x. So are we stuck here? Well, there's one more thing that you learned. If you remember in the alternating series section, this is alternating series clearly because of this -1 to the n. E is always positive, right? So this makes a changing sign. In the alternating series section, when you were learning about the error and all that, does this hopefully ring a bell now or give you a clue as to what to do? The maximum error is the first omitted term. Do you remember that? Okay, so we can use that to our advantage here as well. If n equals 2, what's the term? When n equals 2, it'll be -1 squared, which is positive. It'll be e to the -8 power, okay, which is this in decimal form about there. So that means, since we know for alternating series, the maximum error is the first term omitted, if we sum up only the first term, so if we only sum up n equals 1, that term, the maximum error would be this guy right here, 0.000335. The problem requires a precision of 4 decimal places. This is not quite there yet, okay? Because it's accurate to around 3 decimal places, right? But not 4, okay? Now if we sum up one more term, so we sum up the first term and the second term, that means the maximum error is the third term. So if n equals 3, the term is e to the -3 cubed, so e to the -27 power. If you put in the calculator, it's about 10 to the -12. Very small. That means, again, if 2 terms were summed, this 10 to the -12 would be the maximum error, which clearly meets the requirement of 4 decimal places. 4 decimal places is 10 to the -4. Okay? So the approximate sum, therefore, is the first term is when n equals 1, so it'll be -e to the -1, and n equals 2, which is e to the -8. And you should punch this into the calculator. I forgot to do that, but that's the approximate sum. How about this one? Can we find the sum of this one? Or can we approximate it? This one we can find. This is a telescoping sum. So remember, not too long ago, I said telescoping sum should be like partial fraction decomposition. This is in partial fractions already. So we start going term by term. So n equals 1, we get 1 over 1 minus 1 over 4. N equals 2, you get half minus a fifth. N equals 3, you get 1/3 minus a sixth. N equals 4, 1/4 minus 1/7, so on, so forth, okay? So you see that this -1/4 and this 1/4 would cancel. This -1/5 and this 1/5 would cancel. This -1/6 and this 1/6 would cancel, okay? The terms that don't cancel are this 1, this half, and this 1/3. So that adds up to 11 over 6. Okay, so again, whenever they ask you to find the sum, especially the exact sum, it has to be something you know. So in AP Calculus, you probably learned geometric series, right? You learn those Taylor series, e to x, sine x, cosine x, and you learn telescoping sum. Those are probably the methods you want to use what the techniques you want to use, the piece of information you want to use to find the sum. If it's approximate, there's a few more things like alternating series. You can learn about the Taylor series, the Taylor's inequality, the error bound, and all that stuff as well. So you got to think of what you learned if you get stuck. It has to be one of those things that you learned, not something new. Otherwise, they wouldn't put it on the test. Okay, number 8. This is the last one, but this is multi-part. And it's actually, in my opinion, a pretty good question because it really requires you to use different tests to prove the convergence or divergence of this, okay? So this asks to prove the convergence or divergence using 4 different tests. This really goes to show that a lot of the times, more than one test can be used, and usually one is easier than the other, okay? So what are 4 tests we can use to do this? So go ahead and try to find 4 of them first on your own, okay? We can use the integral test. This is a decreasing sequence, 3 over pi n cubed. I even showed it here. We take the derivative. It's this right here, and clearly it's negative for n is greater than or equal to 1. That means it's decreasing. Okay, and if we evaluate the integral, we get 3 over 2 pi. Okay, so clearly it's finite. So since the integral converged, this guy will converge as well by the integral test. That's one method. Method 2, we could just realize that this is a p-series. Right? If we just pull this 3 over pi out, it's just a constant. This is a p-series, so p equals 3, and we know p-series converge when p is greater than 1. So this will converge as well, or because of that. Okay. The reason I put this as test 2 is this is what the test prep book actually said to do. However, if you remember how we derived this p-series thing, we derive that p greater than 1, then it's convergent. It's from the integral test. So really, this is just a shortcut of the method 1 that we just did. This is a shortcut of the integral test. We can also do a comparison test. Hopefully you would agree that 3 over pi n squared is greater than or equal to 3 over pi n cubed. Our guy is on the right-hand side. This guy, just imagine as n is growing, you're going to be dividing by something smaller over here versus over here, because n squared is growing not as fast as n cubed, right? So if you're dividing by something smaller, your final value is going to be bigger on this side, okay? Now, since this guy we know converges is p to the p equals 2, and our guy's even smaller than the thing that converges, our guy's going to converge as well by direct comparison. Okay. Here's another way to prove the convergence of it. And we can also do the limit comparison test. Okay. We can compare with 1 over n cubed. So we do the limit of this guy divided by this guy. You get 3 over pi. Okay. And since this is finite and positive, both series converge or both series diverge. We know this converges is a p series, p equals 3, p is greater than 1, right? So since this guy converges, our guy converges as well. Okay, this, again, I think is a pretty good problem to really exercise your knowledge of different tests on this exact same series. And you should get the same answer for all these different tests, which we did. Okay. All right, that's the end of this problem set. Hopefully it was helpful to get some additional practice in if you followed along, and hopefully my explanations were helpful if you got stuck on any of them. As usual, please like and subscribe if you found this helpful in any way, and hopefully I see you in another video as well. Bye.